Hello and welcome to Chat with an Astronomer. I'm Laila, and today my guest is Sven Heydenreich from the Argelander Institute for Astronomy. He's doing his PhD there in the field of gravitational lensing and cosmology, and I'm really interested to learn more about that. And I'm also quite interested in this conversation because Sven actually started out not doing physics but math, and then from math transitioned to astronomy, which I think is really and maybe slightly more unusual way to come to astronomy, but still a very interesting one. Hi, Sven. Thank you for being here.
Hello, good morning. Thank you for having me.
So my first question is, how did you at all become interested in astronomy?
That was kind of a long journey. After my high school, I knew I wanted to do something with physics, math, engineering, something in that direction, but I had no idea what to do. So after quite some time of thinking about it, of visiting different universities, I decided to study math. And I really liked it, but towards the end, it became very, very theoretical. So you don't try to describe reality. You describe some fantasy that you make up yourself. You have some rules to make up this fantasy, but in the end, you imagine some things and then analyze the properties of these imaginary things. Sometimes by accident, it actually has a connection to reality that can be used. And then it's completely amazing, and it amazes me every time. But it was just not for me to work on something that doesn't even describe reality. But I did want to work in science. So what got me interested into astronomy was a young graduate trainee position at the European Space Agency. They are posted yearly for people that have graduated their masters. I didn't get it, but still it got me hooked to astronomy. It got me hooked to the things that people do in astronomy and the fascination of studying the universe. So I wanted to do a PhD in astronomy. I called Professor Schneider, who is now my PhD supervisor, and asked him for a position. And he said no. He said, I'm not taking someone who has like zero background in astronomy. So you would have to do a master's in astronomy before. So I did that, and now I'm doing my PhD here. So everything worked out how I hoped it would work out. Just took a little detour.
It's really interesting that you had these two times someone saying no to you. First for the ESA application, and then when you asked Peter Schneider directly for a PhD position, he said no, but still you persisted in your path.
I mean, he didn't say no per se. He said more like, yeah, I'm not taking someone who has zero background, so you have to have some background. So I got that background.
Do you think it was worth it going into astronomy instead of math?
Yeah, certainly. I sometimes miss math, the way you work there, because it's purely theoretical. You don't have computers, you don't have calculations, you just have a paper and a pen, and you sit there and think about things. That is something that I still enjoy doing. But yeah, I love that astrophysics is rooted in reality. I'm getting paid to study the universe. Like, it's amazing. It's
But also, I would assume that your math background probably helps you in some areas.
not as much as I had hoped, to be honest. Because, yeah, as I said, like the things that you do there have nothing to do with reality or with practical applications. So there was no direct help, but the way you think is very, very similar to when you want to solve a problem in astrophysics.
So you're working on gravitational lensing and cosmology. So what is the big question that you want to help answer with your research?
Personally, I'm very, very fascinated by gravity, by the concept of general relativity, because it is one of those things where a very, very high level abstract mathematical concept actually is deeply rooted in reality and can be used to describe gravity to a level where we're still saying, okay, most of our observations, I'm not claiming all of them, but most of our observations confirm general relativity. Maybe this is the final answer. Maybe general relativity is the correct way that gravity works. But maybe it's just a stepping stone, like Newton. Yeah, maybe we will find a refinement of general relativity, or maybe this is the final answer. We don't know, but I would love to contributing to find that out.
Yeah, it's really, really, really fascinating. So what is it that you're studying?
I'm working in the field of weak gravitational lensing. In weak gravitational lensing, we observe very, very distant galaxies that are billions and billions of light years apart. And so their light, when it comes towards us, travels through the universe. During this travel, the light gets affected by gravity, like everything else. Gravity is basically an attractive force that also affects light and bends those light rays. As a first effect, galaxies that we observe are not actually at this point. They are somewhere close by there, but their light has been deflected. So they are not where they appear to be. And another effect that is a bit smaller is that also their shapes are distorted. Well, when we look at one of those galaxies, the galaxy is just slightly distorted. When it was round, it became a little bit elliptical, but we don't know if it was round before. When we just look at one galaxy, we have no way to find out how it really looked like. Consequently, we also have no idea how gravity affected the light of that galaxy. But we have one assumption in cosmology, which is called the cosmological principle, which basically just states that we are not special in the universe. And that also means that there's no preferred direction in the universe. So galaxies, on average, are round. Some might be elliptical in this direction, some might be elliptical in this direction, but on average, there's no preferred direction which they are elliptical to.
Because if they were all oriented in the same direction, then there would be a preferred direction, and then one direction would be special.
Would break the cosmological principle that every place in the universe is the same. When we then average over thousands or millions of galaxies and we see a preferred direction, then we know that this must be due to gravitational lensing. So what we then do is we say, okay, galaxies that are close to each other on the sky and send their light that gets observed by us, this light also traveled through very, very similar matter structures. Basically, what we're doing is we're doing a statistical analysis to quantify this similarity. And from that, we can then determine how much matter there is in the universe and how strongly clustered it is.
So you basically measure how the matter is distributed in the universe.
Yes, basically. At the same time, we're also weighing the universe. So we're determining how much matter in total there is in the universe.
Yeah, and from that you can then find out more about how gravity works and how the universe is, how it is today, and
hopefully. I mean, of course, gravity plays a very, very large role in weak gravitational lensing because we're analyzing the properties of light rays that get deflected by gravity. So all the theory, all the models we do are based on general relativity. So we cannot really use this to analyze different gravities. And it's not that simple to change it. It would be possible, but you would have to develop a new theory of gravitational lensing. But what we can do is we have a quite simple model of how we think the universe works. And this model has so-called free parameters, which are, for example, the amount of matter in the universe. So when you fix the physics and you leave free these parameters, then you can analyze different observations and try to determine these parameters. And when you do that with independent observations and you get the same range of parameters, you can be pretty certain that your model is correct. So for a long, long time, this standard model has provided excellent predictions and everything was in agreement, basically. But now we're getting at a level of precision where we're starting to find some tensions. There are two parameters in the standard model where observations of the very, very far away universe disagree with observations that are made in the more local universe.
Well, that's interesting. That means that maybe something is wrong with the model that we have if those measurements don't agree with each other.
Yes. Well, I mean, it might just be a fluke. These tensions are right now at a level where we say, okay, it's unlikely that this is a coincidence, but this could be a coincidence. But if it's not an error, and if now with the next generation of experiments, we confirm these tensions and they actually rise to a level where we say, okay, this cannot be a coincidence, then we know that something's off with our standard model. Maybe it's something with gravity. Maybe it's something else, because the interesting thing about astrophysics is when you look far away, you also look into the past. So right. Maybe we also have something that was different in the past than it is now. And yeah, first have to confirm these tensions, but then we have to find out where they come from. And that's going to be very, very exciting. And I hope that I can take part in that.
That's really, really exciting. Yeah. Learning how the universe really works. It's really, really interesting. So how do you do your research? You're not an observer, I assume?
No.
You're coming from Mars, so you're more of a theorist?
Yes, I would definitely consider myself a theorist. I am notoriously bad with experiments. We had these laboratory courses here in our masters, which yeah, I'm not going to talk about this. This is so yeah. I would consider myself a theorist, but of course, compared to math, it's still much more applied. So what I do now mostly is I sit at my computer and program. I'm trying to apply new statistical methods to our data to really extract the full information content. And for that, I have to code those methods. So that's what I'm mostly doing: developing code, testing code, or then running this code on simulations, doing statistical analysis. That's probably the majority of the time. And of course, reading what other people have been doing. That should always be a large part of your day. And I'm trying to make it that, but it's still a bit hard for me to keep up with what other people have been doing, because there's a flood of information. Like you cannot read everything.
So much happening, so many new papers every day. Yeah. Is there something that really surprised you during your work, or maybe in astronomy in general, because you were not originally from astronomy, right?
The thing that surprised me most is how little we know. And that is mostly due to the fact that, or I believe that the main reason why we know so little is because it's so hard to determine distances in astronomy. I was not aware of that. Had I thought about it, I would have probably at some point arrived at the same conclusion, that it's very hard to determine distances, but I never did. I mean, we can do a little exercise. When you look at a star, how do you know how far it is away? It's just a point in the sky. In the world, when you want to determine how far something is away, you can either take a ruler and like put it to the ground, measure how far it is away. We cannot do that. Or you take a laser pointer, you point it at the tree or whatever, and measure the time that the laser like needs to bounce back. But those are things we cannot do. When we would like illuminate a star, it's very hard to illuminate a star in a way that we can measure, because stars are kind of bright.
And then it will also take years until the light comes back. So
in cosmology, when galaxies are really billions of light years apart, the time it would take for a radar to come back, like, yeah, our Earth would not be there anymore. So we have to come up with ways to measure distances. And yeah, it's a very complicated thing to do. And I think that's what surprised me most.
And it sounds so easy. Just how far away is it? It's just... what advice would you give to someone who would like to study astronomy, maybe coming from a different field as well?
Go for it. It's worth it. You definitely need some some knowledge of math and physics, because those are tools that are used in basically every natural science. You will need to learn some programming, but not at the level of a computer scientist or anything. You need to tell the computer how to do your calculations. That's it, basically. Yeah, so the base knowledge that you need is actually not that big, I would say, because it's a very, very diverse field. You can go into stellar evolution, you can go into cosmology, you can go into galaxy astrophysics, hydrodynamics. You can say, okay, I don't really care about the physics. I'm going to write codes for simulations. So I'm going into basically almost a computer science approach of astrophysics. And that is why when you start studying astrophysics, people don't expect you to know all of these things, because you specialize during your field of study. So it's more important that you really have a passion for doing this, that you're willing to work yourself into an area that you have heard absolutely nothing about before you came here, basically. Yeah, this fascination and the willingness to be honest, to also suffer some frustration is way more important than any previous knowledge that you could have had, basically.
I think that's right. Yeah, passion is much more important than pure knowledge because you can always learn things, but you cannot replace passion. No.
Yeah. If you have this passion, then you will also like it. So that might be my advice.
Yeah, thank you very much for your time, for this conversation. I had a really, really fun time.